Well, thank you very much for giving me a chance to talk here. And I'm going to present a work that took us a lot of sweat and still full of holes. So I hope that you're going to forgive the holes and see that maybe there are some interesting aspects, and I'll let you judge. So it's work with Martin, Ishan, and David. And I should point out that despite the youth, their role in the conceptual evolution of this work is absolutely huge, not just And so I'll start by explaining why I want to do this and what it is exactly, and then go to some related work to show how it connects to a lot of other ideas that are at different level of acceptance. Then look at the linear problem, because this is one on which we can do some simple mathematics that are enlightening. A small toy experiment that shows that this is not completely stupid, it can work. And then some discussions about problems and limitations, which I find annoying. So let's see, why does it start? You know, the main role of machine learning is to treat problems for which you have no abstract specification. It's not accounting, for instance, where you know exactly what you want to do. It's not an arithmetic problem. It's trying to recognize whether an image represents a mouse or a piece of cheese, and there is no specification for that. And there are two ways to go. One is to construct a heuristic specification. A mouse is something with big ears, and big ears can kind of circle in the pixels, and write a program that targets the specification. That's classical computer vision. The other way is to define a statistical proxy problem, get a lot of data, and solve that. That's the learning approach. And the world domination plan is that when data becomes large and the compute powers become large, defining heuristic specifications becomes harder and training becomes more effective. So this is a nice plan, except that it has a big flaw. And the flaw is that the statistical problem is only a proxy. So here is an example that I found quite shocking at the time. So that was 2014, we were working on the Pascal-Vogt action recognition problem. The task is to say whether in an image somebody is placing a phone call. And the system is you have a bounding box, an image, and you're supposed to give an action label. The bounding box says where the person is. We got the state of the art, we were quite happy. And then Maxime, who was the young guy doing this, came back saying, you know, we got state of the art, but it really doesn't work. Look at this image. So there is a person here, and the bounding box is here, but here you have a row of payphones. You know payphones, right? Yeah, a row of payphones. And if you put the bounding box here, it says not giving a call, which is correct, not placing a call. And if you put it here, it says, oh, placing a call. And in fact, we found out that this system, even though it was state-of-the-art according to the benchmark, only says when there is a person on the phone in proximity. And it's actually correct. In a typical data set that you get from the web, when a person is near a phone, it's usually calling, because these are the interesting pictures. It's a selection bias. And it's correct, it's completely missing the point. This is not what I want. So somewhere between the problem I want to solve, detecting the action of calling, and the statistical proxy, there is a gap, and this gap is playing a big trick on me. Now, in the 90s, when we would do some machine learning, we would carefully curate the data sets. All the data sets were designed for actual deployment using a lot of care in trying to make them representative and everything. Nowadays, it's not possible, it's just too big. And the machine learning algorithms are going to take advantage of any spurious correlation, whatever it is. This is a big problem that has been identified by a lot of people. Like there is the Toralba first paper about computer vision on several data sets, where it's easier to recognize from which data set an image comes from than recognizing a class by training on one and testing on another. There's video question answering. I'm not going to speak to it much. There is all the situation where you have causal feedback loops, which happen a lot in actual economically important areas. And there is one that, for example, adversarial exams are not bugs, they're features. That's the talk we heard from 2 days ago. And well, I'm going to make a conjecture about this one. See, that's a dog. That's Alexander Madoui's dog. And this is the guy taking a picture, and he knows how to take a dog picture. To take a dog picture, you have to have a short exposure and everything, because the dog moves. And, but if you take a cat picture, it's going from too close, the zoom is going to be different, the exposure is going to be different, because this is how you take a nice picture of a cat. And everybody uses the same camera anyway. Now, when you do this change of the camera, you get a lot of little changes that are not very visible to humans, like signal-noise ratio. The texture of the noise is different because the way the sensor is used and the zoom effect. The color balance can be different. The depth of field is different. You see there is a depth of field here. The perspective is different. And these are all things that the CNN likes to exploit. This is much easier to model than model geometry. To model geometry, you have to do something across layers. This, you're going to capture it in a single layer, provided it's the right level. And what this means is that when you take something like ImageNet, the nice pictures get selected from the web, well, you're going to have this kind of biases, and this kind of biases can get you completely wrong. So, what are spurious correlation, and when do we say they're spurious? They're spurious because we don't expect them to hold in future use cases, which might be different from the data collection. And what informs this expectation? So you can have a lot of substantive knowledge that you get from, let's say, scientific models of how the thing works, or past observations that inform this scientific knowledge. And because it's about scientific knowledge, it's interesting to look at a concept that's very strong in epistemology, which is that you want to find stable properties. You want to find scientific knowledge is made of properties that are stable. They're not going to change when you change little things in your system. So, we do not expect spurious correlation to hold in the future. We know this because they did not always hold or hold in the same way in the past. But this is what we do. We collect data from the past and we get the spurious correlation. So what takes? And in fact, you have to remember something, that nature doesn't shuffle the data, we do. We do it because we think that to learn we need RID data, so we shuffle, we split training and test, and we go on. But data is collected at different points in time and space, different experimental settings, different biases. We call this environment. Could be different photographers, different cameras, different whatever. Then we shuffle the record and pretend they're RID. It's a bit of a cop-out. In fact, it's a loss of information if you think about it. So the fact that the data is not RID could be seen as an impediment, but in fact, it's an opportunity. There is information there that we're not using. So a way to formalize this is the way of Jonas Peters and also Nikolai Meinshausen, is to say that the data comes from different environments, E. So we have this environment variable that's going to be discrete. And each environment comes with comes with a different distribution. And we have training set for some environments, and we want a predictor that works for many environments. And nothing says here that the environments we have are random, that have been chosen randomly. It's not a training problem, it's something different. In particular, you would like to see on some environment that something is not stable, eliminate it so that if you have an environment that could be possibly very different, you're still right. Yes?
But if I mean, some and many implies there's a measure on the environment.
They're discrete for now.
No, but like some. Oh, I see discrete.
So just take them as discrete. In real life, it might be continuous and more complex, but you know, I do what I can. I do discrete for now. So a classical move in statistics is to go for robustness. So you have several distributions. I can say I want to minimize the maximum error on my distributions. So minimize the maximum error on my distributions. And then you realize, if I do this, I'm going to focus on the distribution that's hardest and forget the other ones. So maybe I need to add the baselines per environment, because let's say you take pictures of a car in a snowy area in winter with fog, or a picture of a car in sunny California. It's not as easy to recognize or treat. And if you have a system like this, so now it's going to be very simple because my E are discrete. Well, you can rewrite it as a constraint optimization problem, argmin of m subject to, for all e, m is greater than this, the same problem. You can apply Caron-Kutzstucker, and you get immediately that there are coefficients lambda positive, such that the robust regression is a first-order stationary point or a proper mixture of the errors. So basically, I reduce the problem to finding the right mixture. Sorry. So let's look at this. I have 4 distributions, and I want to be good on all of them, which means I'm going to be good on any positive mixture of them, anything that's inside their convex hull. And to achieve this, I can mix with the right lambda e and solve for this. I'm going to get my solution. The lambda e, I can get any lambda e I want depending on how I set the baselines. So in fact, finding the lambda e or defining the baselines, which are a bit of an arbitrary problem, I can make them exactly the way I want. Now the problem is that if I have a distribution that's outside, so it would have negative barycentric coordinates. So it's possible. It's not always simple, but it's possible. And I have no guarantee on this one. And why is it important? So take an example. Search engine query classification problem. And if you look at the distribution on successive days, you're going to see that most of the queries are the same and come with the same probability. Some of them are increasing, like there could be an increasing probability query these days, like which is IIS workshop. And decreasing with decreasing probability, like back to school, because that was just a couple months ago. And something like orange juice, they don't change. And our distribution for the 4 days, they're all here, right? So if we do robust, we're okay on this blue zone, but we like to be okay because these ones are going to become more important. In the future, they're going to come. So we need to extrapolate in that case. And it's not the same high dimensional thing. This is a low dimensional business here. I just took a couple distributions and I go. So I go back to my following example and I can take 2 sets of images. The first set could be images that come from, let's say, from the web, they're pictures. Other things are framed from a movie. And if you look at the movies, you probably have the same selection bias, that a segment of a movie where there is somebody near a phone is probably a segment of the movie where the person is calling. But if you take all the frames, they're going to be before the call and after the call. So you're going to see a slightly different proportions of static images in which the person is near a phone and giving a call, or near a phone not giving a call. So in these 2 distributions, what you can see is that the spurious correlation between the proximity of the person on the phone and the act of calling exists in both, but with different strength. So if they have different strength, you're going to get different regressions. And can we learn only what remains invariant across environments? Because this spurious correlation has different strengths and it's changing, it's not a stable relationship, I want to get rid of it. So let's look what this means. I'm going to say, I want a strong requirement. I want to simultaneously minimize the error in each training environment. For all environments, I want to find an F star that's minimum in all of them. It's not necessarily possible without some help. But let's suppose we do that. What does it mean? Well, if F star is a stationary point, first order stationary point of every error in every environment, it's also a stationary point for every mixture for all lambda that are in R, but they can be negative now. So somehow by asking something that is not a minimum, it's an equality. The derivative is 0. It's a much stronger say to say that I have an equality, and it propagates to other things in a much stronger way. I'm going to show some examples later. So okay, so basically if I have an invariant regression on these 4 points, then it's going to be valid on all my triangle. So somehow it extends the notion of robustness. It spreads much more than the simple robustness, which is a min-max problem. So there are trivial existence cases. For instance, when the thing is noiseless, or when there is actually F star such that the E of y given x is the same in all environments. And in this talk, I'm focusing on what's happening when F star doesn't exist a priori. So my problem is sufficiently different or sufficiently noisy that I cannot really find F star that's the same, that's the minimum of all the problems. And what I can do is playing with the function family. And in fact, here is the idea. I want to find a representation phi of x, such that in that representation, the regression from phi of x to y is invariant. It's exactly the same across environment. So that's the formulation of my problem. And it's a way to formulate the problem of finding a representation that's different from finding the best representation that's going to give me the best error rate. It's different in an interesting way that we wanted to study. And if you think about it, it's about finding the relevant variables. It's an example I take because it shows how crazily ambitious this is. You're observing an apple falling from a tree. And you can look at a lot of things. You can look at the color of the apple, which happens to be correlated with the fact that the apple is falling because the apple has to be ripe. You can look at the number of leaves. You can look at the number of branches. You can look at plenty of things. But if we find a representation in which all falling objects obey the same law, all falling objects you can observe, all apples and maybe a couple pairs, then possibly you understand something useful. So it's about finding the right variables, because whenever you have, let's say, a causal model, you start by giving a causal graph with some variables, and where do they come from? The only thing we have is a bunch of pixels. And we have to find the variable to start with, which is a huge problem. And at this point, I should go with some related work. The first one is the relation to causation. Turns out that invariance is extremely related to causation. And this is something that's been known for a long time that you can see in the work of a number of epistemologists like Nancy Cartwright or Woodward. And the relation is like very simple. If you want to predict how a system is going to be after an intervention, there are only two things you can use. You can use the knowledge of the intervention and the knowledge of properties that you assume are going to be invariant before and after the intervention. So somehow, when you do calculus or Rubin seniorability, they're just mechanisms to tell you which conditional distributions out of the variables you know are going to remain invariant after and before the intervention. And of course, discovering invariant properties is easier than discovering causal graphs. It seems easier. Actually, I'd say the question is still open, but the bet here is that it's easier to find invariant properties than to try to find a causal graph and orient all the arrows, which has been problematic for a while. There is the work of Jonas Peters, the Zurich group, and Nikolai Meinshausen, that was a strong inspiration. And in their case, environments result from intervention on the graphs. They have a causal graph, and they start intervening, and they observe a lot of distributions. They assume the set of variables is known, which I see as a limitation, but still very interesting. And the representation is merely selecting a subset of the variables. And they show that if they find an invariant representation of that kind, then they found the direct causes of y, which is the variable trying to predict, and a number of assumptions that I'm not going to detail here. Another thing that's quite popular these days is adversarial domain adaptation. And it's about the same kind of idea. You have a classifier, and you have different domains, and basically what you do is that I want to classify, but at the same time, I want another classifier that tries to recover the domain label or the environment to be ineffective. You're saying from the hidden layer at some point, I don't want to be able to say from which environment this data comes from. And that's very connected to the Toralba force thing, but they show that you could classify from which data set an image comes from. And they're trying not to do that. And turns out it's too strong, because if you say that if I'm a features F, and from there I cannot classify the environment better than chance, it means that the distribution of the feature doesn't depend on the environment. And that means that P of any function of these features doesn't depend on E either. So the class labels you predict cannot depend on the environment, even though in different environments you could have different distribution of class labels. And there are plenty of tricks, conditional, ladder, and everything to try to lower this. And in a sense, the criterion we propose. I thought you would tell me 4 minutes, and I was stressed. The criterion we're proposing here is one of the weakest of that kind. And finally, there is the robust approach, which is to say, I want to minimize the supremum on some ball of distribution that's around the observed distribution. It could be a KL ball or a Wasserstein ball. And it could be the KL ball or a Wasserstein ball. And the difference is that we use multiple environments to define the ball. We don't assume the ball has a certain shape a priori. and we invoke invariance to achieve robustness well beyond the convex hull of training environments. Or at least this is what we hope. So now I'm going to discuss the linear case. So in the linear case, both the feature extraction and the regression are linear. So that's a matrix. Find a matrix S so that V simultaneously minimizes, let's say, the least square error for all environments. And because it's linear, the overall regression is linear too. And there are some issues, like you can easily see that there are a lot of uninteresting solutions, like S equals 0. What matters is the null space of S, because you can balancing between S and V pretty easily. And you see that there are some non-continuity, like if the null space of S is what really matters, which represents the information you're going to censor because you consider it carries spurious correlation. If you change S just a little bit, it's not going to be singular anymore, and the null space is 0. So you have some continuity. You cannot just optimize that directly. You have to do a little bit of linear algebra. So the linear algebra is here. Basically, there are two parts. The first part, first of all, it doesn't treat about V and S, it treats about W, which are the total regression. And it says that W can be decomposed as S transpose V, where S is a representation matrix and V simultaneously minimizes all the errors, if it's orthogonal to the gradient across for all environments. So it's orthogonal to the subspace spanned by the gradients across all environments. And then when you have this, the matrices S, all of them, for which the decomposition exists, are those where null space is orthogonal to W and contains all the gradients. So what does it mean? Let's take least square. The criterion here is in fact a quadratic criterion. So basically for each environment, you have an ellipsoid. And the intersections of these ellipsoids are the points for which you have invariance. You have a trivial one, which is 0, and then you have other ellipsoids. So it's not good news, because intersection of ellipsoids are non-connected. So it's not going to be that simple. You see that if you have D ellipsoids, where D is the number of dimensions, the solution is a discrete set of points. So in fact, it can be quite precise, but if you have less than D, you have a lot of solutions. Then you can look at the rank of the feature matrix. And one thing is the orthogonal projection, it's not orthogonal in that case, I changed the theorem. So now S must have the gradient in its null space. That means the null space, if the gradients are in generic position, contains M gradients, has to be dimension M in generic position. That means that in general, the rank of S is going to be less or equal to D minus M. But in general only, there might be solution which is higher, like high rank solution exists when the gradients are linearly dependent across environments. In that case, you can say there are coefficients lambda e, not all 0, such that the sum of the lambda e gradient equals 0. That's the condition to have a high rank solution. And when you do this, you can easily see that W is a stationary point of sum of E lambda E C E W. Except that lambda E is not constrained to be positive, they're going to be negative. So you find again the idea that sometimes you might want to do negative barycentric coordinates in your mixture space to get something interesting. And the consequence of this is that you can exactly recover high-rank solutions. Let's say you have two sets of environments. E all are all the environments on which we want to be good. And we're going to assume there is a unique invariant solution, non-trivial, not 0, of rank R there. And each n are the M environments we know at training time. So if M is greater than D minus R, and if they're in generic position subject to the constraint on E all, which is technically you have to nail it, it's not so easy, the only invariant solution on ETR of grand greater than R, they form a discrete set. Because when you take all the equations together, you find that the solution, the number of equations, number of unknown is the same. And the solution E all is one of them. But in fact, if you get one or two more environments, you're going to find the solution uniquely. And if you work out what it means to say generic position, you see that if M is greater than D minus R over D plus R, you uniquely reconstruct the single solution, which is sort of shocking. And it's not because it's linear, because most of it is actually in discussing the number of equations and the number of unknowns. So basically it means that you don't need to have environments that are taken randomly from all the ones you could observe. You just need to have environments that exercise the spurious correlation you want to get rid of. How much time do I have? Just 10 minutes?
Yeah, 10 minutes.
Okay, minimal example, blah, blah, blah. It's interesting, but I can't do it. Except that you can see that you get mixtures that have negative coefficients.
So do you know which data comes from which environment? Otherwise, how do you do it?
Yes, you know, you have data sets from a number of environments, not that many, and you want to find something that's going to be robust across a much larger set of environments.
And then within an environment, you're going to, again, use IID.
Using an environment, I'm pretty much IID. I'm minimizing an average within the environment, but I want the minimum to be the same. And so far, we haven't made a lot of considerations of finiteness of the training set, which is an issue. No. So another way to look at it is to say, we optimize something, we want to go towards one of these intersections. So we can just write a regularizer for this, something like the orthogonality criterion squared, and want all these things to be 0. Doesn't look very nice because in terms of optimization, it's going towards something very spread apart, but we can try. And you find something amusing that if you actually insert a dummy multiplier after your linear system, the derivative of the cost with respect to this multiplier is exactly the orthogonality condition. And the way to understand this is to say, suppose I have my system and I add an adaptation layer that's supposed to adapt for each environment, that I could train separately for each environment after training on everything. And you're saying that if essentially the derivative says that, you know, I don't need to adapt it, it's good already. And for each environment, you essentially realize the necessary and sufficient condition. And that's interesting because you can view it that way even when F is a nonlinear business. And in fact, you can take part of the linear analysis and try to make it nonlinear, but it's painful, but it's doable to some extent. So let's do that. So there is a data set that we call colored MNIST. It's essentially the MNIST training set. And we have two classes, which are the low digits and the high digits. Low digits 0 to 4, high digits 5 to 9. But for a reason that I'm going to become clear later, we're adding a lot of noise. We're adding 25% label noise. So basically, on the basis of the shape of the digits, you cannot do better than 75%. Then we color the digits, and we color them according to the label, but with either 10% or 20% label noise. That means that the color of the digit is a better indicator than the shape, except that we have two environments, one with 10% label error on the color, and the other one 20%. And we're going to train with the reverse color scheme. What we want to achieve is to build a system that, because it has access to two environments that exercise slightly different association between label and color, is going to eliminate completely color from the system and rely only on the shape, even though the shape is slightly inferior. And basically, if you minimize the empirical risk, you mix data from both environments, you get something like 85% pretty much, which is the average thing. And when you reverse the color, well, you get a catastrophe. If you add this regularization term and play your numerics right, which is tricky, you get something like pretty stable. Why not 75? I know this. We think we should be able to get 75, and we're not able to, but the numerics are pretty painful. So anyway, this is a toy example, but also a proof that it's possible to use a slight discrepancy in how spurious correlation affect the label in the training data to actually completely eliminate it. And well, okay, so these are just the outputs of the network. When you train with normal empirical risk minimization, you see that the reverse color scheme, it just goes the other way. And when you train with IAM, you see that it's been largely put in line. Now, I want to scale this up. And you have several problems there. First one is numerical issues, because the regularization term is very non-convex. And the second one is that realizable problems are very different. We use a lot of label noise. And all the representation scheme, the representation construction scheme that I described is conditioned on the ID that you cannot find the F star that's going to be optimal for everything, for all environments, and that you have to find the right representation. But it turns out that when you take real data, or it's the real data that people like nowadays, well, it's not like that. You can achieve 0 error on everything. You can overparameterize, you can get 0 error. So if you look at what's happening typically in the data we collect, we have what's happening in the world, and there is something I call the pre-label, which is what we're interested in, affects things in the scene, and we get an image. And we want to find the pre-label, so we ask labelers to produce the pre-label. So the labelers are looking at the image, they're producing the post-label, which is not exactly the same. Like if you take the action of giving a call or placing a call, if the person places a call in hiding, it might be that in the real world it's placing a call, and the consequences of placing a call are going to happen. But in the labelers are going to say no because they can't see it. So they're slightly different. Now the trick is, not to self, yeah. The trick is that the labeling process is often designed to be as deterministic as possible. We train the labelers to try to give the same answer for the same image all the time. Or we pull them to try to achieve this. Which means that there is a F star that's going to be optimal for everything. And if there is a F star that's optimal for everything, all my criterion for finding a representation is vacuous. So the good side here is that you get invariance for free. The bad thing is that my criterion is not that interesting anymore. It has to be refined or expressed in a different way. So instead of looking at the error, look at how I'm selecting the solution. So basically, it moves from the cost function into the regularization, implicit to explicit. And so this is something we have to sort out. And that's the biggest hole in the work. Anyway, the conclusion is that the statistical problem is only a proxy. And if we want to solve the famous AI problem that is so overhyped, we're not going to do by just using proxy if we don't understand what's between what we want to do and the proxy itself. And there are lots of things in that domain. The second one is that we shuffle the examples, maybe we should not. We're losing information to make the data resemble our current theory, but maybe it's a bad idea. That the idea of invariance across environment, exact invariance, is not the same as robustness, and it buys extrapolation powers, because asking an equality is much stronger than asking for minimality. And that's very connected to causation, and we know this from the work of epistemologists. Invariant representation can enable invariance, but we need to do something else for the frequent realizable cases. And in the end, this is far from cooked, but we worked on this for 1.5 years, and we thought it was time to talk about it, even though it's far from finished. Thank you.